Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Hello everyone, welcome to this lecture, and today we will pay our attention to the topic on fatigue. Okay, though we have seen this phenomenon along with fracture mechanics. In fact, we looked at elaborately on the crack growth aspects in terms of Barrett's law, and we also looked at the fatigue thresholds, crack growth, and environmental effect, and various crack closure mechanisms. In fact, all the design related aspects of fatigue we have already seen along with the fracture mechanics. But in this lecture, at least I want to look at the other aspects, whatever we have not yet touched upon. In fact, we will start from the very historical background and basic definition of fatigue and so on, just so that you'll have a complete information about this topic. So 90% of service failures are due to mechanical causes. That is why we are interested in fatigue. What you have to understand here is, though the tensile test or typical tensile test gives an idea about the yield stress of a material or yield strength of a material, and when the material is subjected to cyclic loading or multi-axial loading, the material will fail much below the yield strengths or yield stress. Okay, that's why we in fact study all the mechanical behavior in detail. Like for example, creep, the high temperature deformation, and biaxial loading, triaxial loading, right? And then with the environment, without environment. Okay, so all these aspects, okay, they are going to the material is going to respond to the external loads or a type of external loads very differently. That's why we study all this different aspects of mechanical behavior. Okay, like tensile, impact, creep, fatigue, fracture, and so on, right? So vibrational stresses in turbine blades, for example, is a typical examples by which the failure takes place through fatigue. In fact, we have seen this in the fracture mechanics lesson. One of the blades we have shown is the turbine blades, where the fatigue crack growth was shown. Alternating bending loads on the blades and shafts. This is most of the rotating body, whether in any engineering setup or even the vehicles, automotive vehicles. These are all quite routine components which subjected to alternate bending loads. Okay. Fluctuating thermal stresses during start-stop cycle and due to power changes. So this is also another source of cyclic load. Okay, not necessarily mechanical, but we are talking about thermal fatigue. Okay. Automotive drive axles, crankshafts, paper clips, very day-to-day examples, I-beam of cranes, and bridges, where you see the variations in the bridge, traffic density, offshore structures, and stress plus seawater corrosion, aircraft structures, various air pressures, temperature gradients, about 3 kilometer altitude, below 0 degree centigrade temperature will be experienced, and 10 to 12 kilometer temperature, minus 50 degree temperature will be experienced, and up to the landing temperature may be 30 to 40 degrees centigrade. Humidity also changes. So the aircraft is one classical example where you have all type of environment. First of all, cyclic loading plus stress corrosion, cracking environment, and then temperature difference depending upon the altitude. So that is why we emphasize the crack growth problem and the crack nucleation problem. We elaborately discussed in the fracture mechanics because of this aspect. And even implants in a biomaterial. Most of the biomaterial, the classical one is the hip joints. They are all subjected to fatigue loading. So this is we know. And we will look at what are the different forms of fatigue damages, and the one which we generally talk about is mechanical fatigue, where a mere fluctuations in the externally, excuse me, externally applied mechanical stresses or strain is considered. And the thermal fatigue, where the thermal stresses, temperature fluctuations only considered. Example is filament bulk. And there is something called thermomechanical fatigue, where thermal plus mechanical fatigue, they are combined together. That means mechanical fatigue happening at very different high temperatures. Okay, a typical example is solder joints. Corrosion fatigue, fatigue in corrosive environments, that is very important. And rolling contact fatigue, where example in bearings, etc., the repeated load applications with rolling contact between two materials. Okay, the rolling contact fatigue is also important on the some of the rails on the top surface. Very important applications. And then fretting fatigue, pulsating stresses along with oscillatory relative motion and frictional sliding between surfaces. For example, a rope in the wire assemblies, the inner inner core wire will be there, and then there will be a shell or cover. They will just move against one surface against the other surface, so inner surface. So that will create a kind of fatigue loading. So you see that primarily you have about 6 type of different forms of fatigue damages. Here we can just look at it. If you look at the historical background, the fatigue is the word comes from the Latin word fatigere, means to tire. So like human beings get tired after some heavy workload, like material also get tired. That's the kind of meaning. And if you look at the definition, fatigue is a term which applies to changes in properties which can occur in a metallic material due to the repeated application of stresses or strains. Although usually this term applies especially to those which lead to cracking or failure. We have to understand that fatigue is a failure mechanism. In fracture mechanics, we describe fatigue as a crack growth mechanism. So that is why it has completely come under the fracture, not deformation. Okay, fatigue and fracture mechanics are closely related. They're in fact 90% overlap, because fracture mechanics considers fatigue as one of the primary crack growth mechanisms. So similarly, here also we will bring in fracture mechanics concepts wherever it is required. We will see. And fatigue is recognized problem with the advent of rotating and reciprocating machines during industrial revolution in 1800. And in last 4 decades, mechanical, microstructural, environmental factors on cyclic deformation has been investigated because of the optical and electron microscopy development. People started looking at PSBs called persistent slip bands, striations, crack closure, short and long cracks, variable amplitude spectrum loads, corrosion, low and high temperatures, multi-axial state of stress, notch fatigue, life prediction methods, non-metallic materials, composites, thin films, nanomaterials, bulk metallic classes. So because of all this, developments, the fatigue has been, focused, has taken into different branches because of the material development, and also the characterization techniques, and also the needs, the special needs, the special environment, and so on. So the fatigue is growing in all these fields. So it is an underpinning phenomenon. Whatever the material changes, whatever the technology changes, you have to study this phenomenon. Without that, in engineering, you cannot do any save the life of the component without understanding this phenomenon. Okay, so that is very important idea. So now we look at what are the stress cycles. The basic idea about the stress cycles. What you see here is a stress versus a cycle plot. So you have the a sinusoidal cyclic stress is shown here. This is a tension axis and this is a compression axis. So this distance what you are seeing is a sigma A, that is you can say amplitude or alternating stress, you can call it sigma A, and this is sigma R. It's completely a reversible cycle, completely reverse cycle. So this is one way of subjecting the cyclic loading. So in this type of loading, what you have to understand is the magnitude of the tension and the compression is equal. So there is no net effect. We will see what is that. What is that I'm talking about? Yeah. So on the other hand, it is what is seen in the first one. If you look at this, it is entirely quite different. What is the major difference? The complete cycle is happening only in the tension region. So it is always tension, but only the magnitude varies here. So this is a sigma max, and this is the mean stress, sigma mean. You can see that sigma mean, and this is sigma complete reversible cycle, and this is a sigma A, alternating stress. Okay, so this is sigma minimum and this is sigma maximum. So that is how it is shown. So you can choose any one of this kind of loading to study the fatigue phenomenon. Okay, but what about the this figure? What does it show? In fact, most of the in real time situation, the stresses will be of this kind. Like any critical engineering component will be subjected to, they will be experiencing this kind of a stress cycle. For example, typically the aircraft wing at the when it flies at the high altitude because of the gusts, right? So this wing will subject to this kind of arbitrary loading. So you can see that there is no constant amplitude here. Suddenly it spikes, kind of a overload, right? This is a overload here, again something like that. So in reality it will be very complex. So that is why whatever we do in the laboratory in the form of fatigue test, it will give some idea. It will never replace the reality. So whatever the complicated cycles you can, if you are interested in studying the material behavior under cyclic loading of very complex cycle nature, so you can create one and then try to evaluate the life of the component of the material and so on. So that's the idea. So yeah, this already I've told. This is reverse stress and repeated cycle, and this is random or irregular stress cycle. And then we will now look at some of the basic definitions. Stress range, sigma R is equal to sigma max minus sigma minimum. So I just said completely reverse stress will have the stress range sigma R, and alternating stress sigma A is equal to sigma R by 2, where sigma maximum is sigma minimum by 2. So this is another definition. There is something called mean stress. Mean stress is sigma m is equal to sigma max plus sigma minimum by 2. And the stress ratio, very important parameter in fatigue, R is equal to sigma minimum by sigma max. So this is called the stress ratio. And there is also another parameter called amplitude ratio, which is designated as A, which is equal to sigma A by sigma m, which is equal to 1 minus R by 1 plus R. So this is some of the parameters which being used in the fatigue chapter or fatigue literature, you will come across all this terminology. And one important parameter which is a characteristic of a material similar to yield stress is the fatigue limit of the material. So typically the fatigue limit is you can see in the stress versus number of cycles to failure plot. For example, if you see the mild steel, the life keep on increasing as the stress comes down, which is quite obvious, but after that it reaches a saturation here. So this is around 10 to the power 7 number of cycles, typically characterized as a fatigue limit. But if you look at the aluminum alloy, the stress keep on decreasing, and as the number of, with the decreasing cycle, the number of cycles to failure keep on increasing, but it is not reaching a saturation, it just goes down. And then we will see why it happens. Okay, it is related to microstructure. You know the phenomenon behind it. We will discuss that. And this fatigue limit is also called as endurance limit. Stress for which material has infinite life, which is generally considered as more than 10 to the power 6 cycle, but in modern days it is not just 10 to the power 6, it is 10 to the power 8 and beyond. In fact, if you look at the literature, people talk about very high cycle fatigue. very high cycle means it goes beyond 10 to the power 8 and 10 to the power 9 and 12 and so on. So we will look at those details. The endurance limit existence is due to interstitial atoms pinning of dislocations, and which prevents the slip. That is one of the reasons people report. And this limit can disappear due to periodic overloads, corrosive environments, or high temperatures. Okay. So what we are talking about is the room temperature deformation here. But when it comes to overloads, which we have seen in the last chapter, and corrosive environment and high temperature, this may not exist. The endurance limit may not exist. Most non-ferrous alloys do not exhibit endurance limit, and hence they use the value of 5 into 10 to the power 8 cycles or some other number much higher than the design life. As I just mentioned, fatigue limit is the design parameter like yield strength. So the material do not exhibit a fatigue limit or endurance limit, and one can consider 10 to the power 8 number of cycles. The corresponding stress is considered as the fatigue limit. So this way of finding out the SN curve, that is stress versus number of cycles to failure, is called stress life approach. Okay, so that is how you should look at it. This is also called stress controlled fatigue, okay, or high cycle fatigue. There are different names depending upon high cycle fatigue, because normally the material reaches endurance limit and beyond, very huge number of cycles. So that is the name comes from that kind of number of cycles. But technically it is a stress controlled fatigue testing. So the stress amplitude is controlled, and look at the life of the component. So it is called stress life approach. Okay, so that is what is shown here. It's the same graph like what we have seen there before. And Wohler reported quite a bit of aspects about this fatigue in 1860, and he conducted a lot of experiments on smooth specimen, plane bending, rotating bending, uniaxial compression, tension, cyclic loading. So you can have any combination of this loading pattern to take this SN curve. And there are standards now available, very well established standards, ASTM standards, E466 or E468, that quite nicely exhibit the code for conducting this kind of test. And this solid line is again for mild steel and other materials which harden by strain aging. Okay, so most of the material, okay, which undergo the strain aging, you know, you have the background to understand this terminology now, they will exhibit a typical fatigue limit. Many high strength steels, aluminum alloys, and other materials which do not strain age or harden do not generally exhibit a fatigue limit. So this is one clue. So, okay, this is closely related to the microstructure, but it is also a characteristic of a material, like what we have just looked at, wavy slip material or planar slip material, and so on. And then you can bring in some other microstructural aspect also. Very many high strength steels will have, which have non-equilibrium microstructures, also will not undergo strain aging or strain hardening or work hardening significantly. They also will not exhibit the fatigue, sharp fatigue limit. So that point you have to remember. So this stress life approach is normally represented by this equation called Basquin relation. Delta sigma by 2 is equal to sigma A is equal to sigma F prime into 2 into NF to the power B. This is very important relation. So the equal to the fracture strength, sigma F is the fracture strength or is a fatigue strength coefficient. You can call it equal to the fracture strength, what we have known in fracture mechanics. Sigma F prime is the fatigue strength coefficient. B is the fatigue strength exponent for the most materials in the range of minus 0.5 to minus 0.12. So that is something you have to remember. And like we have seen in the previous chapter, the fatigue life which we talk about is not, the total life is not, I mean, I would say the total life has got several components. Okay, it is not just represented by one factor. That's what I was trying to say. So the total life contains a crack initiation period and the crack propagation period, and then final failure. Okay, so this is how the endurance limit curve has to be understood like this. And of course, the gap between the final failure and the crack propagation is keep on decreasing as you move close to the endurance limit. Okay. And also close to the, when you approach the endurance limit, the life spent on the crack initiation is much higher. This also we have seen in the fracture mechanics chapter. As you come down in the stress, the time required to nucleate a crack or initiate the crack is much higher. That is a major part of the life, and the crack propagation is much less. So the SN curve strictly pertains to total fatigue life of a defect-free material. Okay. So we assume that it is a defect-free. Number of cycles to initiate cracks in a smooth specimen plus number of cycles to propagate the crack to a final failure. So that's what's shown here. The fraction of fatigue life which is expended in nucleating a fatigue crack may vary, essentially 0% for specimen containing severe stress concentration or surface defects to as high as 80% in a very carefully prepared, defect-free, smooth specimens of materials. So what you have to understand from this statement is, for a fatigue test, you need to prepare very, very careful surface. The surface should not have any defect. Okay. In fact, some people do electropolishing. Right? Electropolishing also will create some surface defect. Some people adopt some etching technique to dissolve all the the grooves which are generated by the turning operation while fabricating the turn, while the specimen is being turned, right? So these grooves all will get dissolved by the chemical etching. Okay, then surface becomes smooth. There are several methods by which you can produce smooth specimen. Then you can see that 80% of the uh, you know life will be exactly spent on the crack initiation. So this is about the general aspects of the stress life approach. For a given material, fatigue limit has a range depending upon variables. Sigma failure is 1% of UTS. Very high strength steels with a sharp notch with the high tensile mean stress in a very corrosive environment. This is some kind of a thumb rule people have reported in the literature. Sigma failure is 70% of UTS, which is medium strength steel in a inert atmosphere with appreciable compressive residual stresses. So this is all some thumb rules in a kind of a shop floor kind of environment people use. I just want to give some reference for that. So there is something called fatigue ratio, which is sigma endurance to sigma U, that is ultimate tensile strength. For unnotched, highly polished steel specimen, sigma endurance is equal to 0.5 MPa for specimen which is having sigma U less than or equal to 1400 MPa. Where sigma endurance is 700 MPa, then you have to have the ultimate tensile strength should be greater than or equal to 1400 MPa. So this is some kind of a thumb rule. And what are the test variables? One primary variable which we talked about is the surface roughness and also stress range. So under these two headings we can have several variables. Under the one is the stress range, and then another is a mean stress, stress ratio R, strain rate, temperature, waveform. So you have about 6 important test variables are possible. So you need to select or fix each one of them for each fatigue test. Okay, and very importantly, finally, environment. Okay, this is again a variable. And if you look at the surface roughness is one term, surface strength, residual stress, grain size, cold work, precipitate size, shape and distribution. Okay. So look at the number of test variables are going to affect the test results. It's quite quite a lot of variables. So obviously, what do you expect in this kind of tests? You will have lot of scatter. That is why fatigue testing is inherently statistical in nature. Fatigue data itself is a statistical data. Unless you have the statistical way of analysis the fatigue data, it's very difficult to arrive at a concrete or a meaningful conclusion. So this is one important aspect you have to remember. Of course, the coating also one of the parameters which decides the fatigue life. So like I just said, fatigue data inherently, it's statistical nature. So let us look at what are the aspects of statistical aspects of fatigue. So what you are seeing here is a very interesting plot. So this is a stress versus number of cycles to failure plots, and then you see that it is actually a 3-dimensional plot drawn in a two dimension. You can see this profile goes and comes down. This is a 3-dimensional profile, and what you have to look at here is this is what is you are seeing is a probability, the probability of the failure, probability of the material failure is plotted, and you can see that this is 1% probability, 10% probability, and this is 50% probability, and this is 90%, and this is 100%. So what you have to appreciate here is, suppose all these curves also will exhibit a kind of endurance limit. So for example, if you take this curve, it will end up in this endurance limit, and this 50% probability is coming in the center, and about 10% probability is here. So here itself you have a distribution of data you have to predict the endurance limit. Okay, so you may have the test which your test may involve a stress level belong to this, and then it may fail within this if it is a higher stress, and if it is a lower stress it may end up here. So even this endurance limit from 10% to 100%, you need to have arrive at a mean fatigue limit. Okay, so that is how, even to create this kind of a plot in a true sense, you require a large number of samples. So it is not like, I'll take my tensile test, one sample, I'll test it, I'll find out all the parameters, then I'll take another specimen to test it again, to look at the range of yield strength, ultimate strength, so on. But in fatigue, it is not that. If you want to really create a complete statistical analysis like this, you require huge number of samples. It is not that. And how much time it is going to? We are talking about each test is going up to 10 to the power 8 or 9 number of cycles, and then we are talking about here about a range of fatigue limits. So one really has to spend lot of time and energy to obtain this kind of a true fatigue data. So now you understand the significance of the statistical nature of fatigue. Okay, so that is the intention here. So this is the fatigue data represented on the probability basis.